Okay, so good morning, good afternoon, good night, and thanks for joining this webinar belonging to the Technical Talks of CTSoc series. This is the first talk of 2026, so Happy New Year. We're still in January, so I still have the opportunity to greet you. I'm Fabrizio Lamberti. I'm the CTSoc Vice President of Technical Activities. I'm also the chair of the Technical Committees Board, and these webinars are part of this series which has been created in the technical committees. So I will just give you a brief introduction of what the technical committees and the technical activities area is. Technical activities are one of the areas of IEEE society, which includes also publications, conferences, industry and standards, educational activities, and technical activities is in charge of as you might guess, organize and coordinate technical aspects in the fields of interest of IEEE consumer technology societies. And the technical activities areas does that through the Future Directions Committee and the technical committees. The technical committees were launched about 5 years ago now, and so far 15 technical committees have been established. Here you can see their titles, and actually they cover the broad spectrum of consumer electronics technology and consumer electronics technology. The technical activities is organized as I said, in the Future Directions Committee. In these 15 technical committees, there is a board which includes a number of representatives from the society, various VPs, plus the officers of these 15 TCs. Each TC has its chair, vice chair, secretary, and a membership. So these are the names of the officers for the 2025 and 2026 term. Each TC has its own website with the mission, objective, the officers, and members. So if you are not yet a member or know colleagues who are interested in joining and becoming a technical committee member, please fill this form in or forward the link or the QR code here to your colleagues, inviting them to join. So far, we do have 1,500 members, and they cover the various areas in different ways because, as you can guess, there are overlaps between some of them. But please note that these are not all members of CTSoc, because this is an activities that goes beyond the boundaries of a society. So this is people that is really found and interested in working in this domain. What is the goal of these technical committees? As I said, support CTSocs in a number of ways, supporting conferences, publications, standard education, history, and here you have the details, but I want to show you through this page what are some of the things that these committees have done, like they propose and identify people willing to serve in technical positions in conferences. They serve and they are selected through call for associate editor positions in our journal and magazines. They organize special sessions in journals. They organize special sessions in conferences. They are involved in a number of initiatives, not only in CTSoc, but for instance, the digital reality, digital privacy, which are initiatives governed by IEEE. They are involved in collaborations with other societies, not just within IEEE. They launched special interest groups like on the metaverse. They are selected as distinguished lecturers, speakers in these talks. They contributed to projects like these internship projects. They working on standards. This is an example of an implementation of the NPI IEEE Metaverse model architecture standards, which has been recently approved by IEEE. Some opportunities that are offered for you to members of the technical committees and the IEEE in general are, for instance, the participation and submission to conferences. I listed here the conferences managed by CTSoc that currently have open call for papers. Zinc in Novi Sad, Serbia. ICIR, this is a conference that is supported by the IEEE Digital Reality, which is participated by 8 societies of IEEE, and this year will be in Italy. ICC Taiwan and GCC Taiwan, which will be in Kobe, Japan. So please submit, and if you're interested in getting involved in the committees of this conference, please contact me. Regarding publications, as you know, we have the Transactions and Consumer Electronics, the Consumer Electronics magazine, which I'm serving as editor-in-chief for, News on Consumer Technology, CTSoc World Newsletter, CTSoc Digital Library and Research Center. Regarding these two publications, let me point you to the fact that there are call for open special issues. So if you are interested, these are the 2 special issues open for Consumer Electronic Magazine. These are those for transactions. And of course, if you are interested in proposing a special issue for transactions, it's closed now, but for the magazine, please, here you have all the information that you need. So finally, talking about the technical talks, as you know, we have had already a number of we already have a number of
我们要听了，please， 对，要听着干嘛？等下怎么走？
Sorry.
I just muted. Okay. And we already had a number of talks. Next webinar will be on February 27. You will receive the details soon after this meeting. Anyway, check the webpage of the technical talks to have more information. But today, we will have 2 great speakers in our 19th webinar. Dr. Muhammad Asif Khan and Dr. Sean Ma. They represent 2 TCs, the TC on Automotive CE application and the TC on smartphone and mobile device technology. Muhammad is from LA, USA, so quite late or early in the morning, and same for Sean, who is from New Zealand. So I want to thank them again for the time they devoted to this and they are devoting to this event. And I would leave this is my last slide. Again, frame with your camera this QR code if you want to have more information. And I would now leave the floor to the colleagues who will introduce our speakers. First of all, I think that Dixon Lee could, Yogesh Marathe, as officers of the CATC, could introduce the first speaker. Thank you.
Thank you, Fabrizio. Hi, everyone. This is Yogesh. I am the chair of CEA+MDT Automotive Consumer Electronics Applications and CTSoc. And I'm very privileged to introduce Dr. Muhammad Asif Khan, who would walk us through his talk. Talk is very interesting. Talks about diffusion models for synthetic data generation in autonomous systems. In today's world, I think there is nothing complete without we being taking a reference to AI and machine learning models. And I think let's test our learning as we go through the talk. Briefly, Dr. Muhammad works as a research associate in Louisiana State University, USA. Before joining LSU, he worked as a research scientist in Qatar Mobility Innovation Center. And he got his PhD in 2020 from Qatar. And his PhD work includes diffusion models, autonomous vehicles, and reinforcement. So over to you, Dr. Muhammad. All the best, and thank you very much for taking this initiative.
Thank you so much, Yogesh and Fabrizio, for organizing this event and for the introduction as well, Yogesh. Let me share my slides quickly. So, yeah, somebody just please confirm if everything is okay with the slides and you can see it in full screen.
Yes, it is up.
All right. So, thank you, Yogesh, Fabrizio again, and everyone who is right now online and attending this event. In this talk, we are going to discuss and I'm going to give you a brief overview of the diffusion models and how we use diffusion models for synthetic data generation, which can be very useful in many applications, particularly in autonomous systems. Due to the limited time, we will not go into more details about the architecture of the diffusion models, but we're going to focus more on how diffusion model works in general and how we can use them for synthetic data generation and what could be the possible use cases for diffusion models in autonomous systems. So we all know the importance of data. We know that all modern data-driven systems need data and they need high quality data. When the data is scarce, when we do not have enough data, the performance is limiting, and that's what we call underfitting in machine learning. And sometimes we have a lot of data, but the data is not of high quality. So when the data is bad, there could be a lot of issues, including bias, missingness, inconsistency, let's say, and this kind of garbage data, when inputted into any AI system, the output is also a garbage. You don't see a good performance. So that's why we need synthetic data when we do not have real good quality and high amount of data. So there are a couple of scenarios which I want to highlight why we need why we need synthetic data in autonomous systems. So for example, in some use cases, we do not have real data available. For example, a traffic accident of different nature in any autonomous vehicle scenarios, we do not have enough traffic accident data, so we might need some kind of synthetic data for these kind of scenarios. Sometimes the real world data cannot be acquired. For example, you have issues with privacy and identity needs to be hidden. So you need some kind of, for example, face sweeping to protect people's privacy. So again, you need synthetic data. And sometimes real world data is available but that is not suitable for the application and use case that we are interested in. For example, you have a CCTV detection system, but there are some kind of missing classes or missing scenarios which you want which you want the system to be operating on. So again, you need synthetic data. Now, when we say autonomous system, we do not necessarily targeting autonomous vehicles. It could be any kind of autonomous system where some of these are listed here on this slide. They can be autonomous vehicles, drones, mobile robots, surgical robots, control systems, or even software agents. Those could be different examples of autonomous systems where we can use diffusion models for synthetic data generation. Now, the types of data in autonomous system, and more particularly because we are focusing more just as a use case on autonomous vehicle here in this presentation. So the types of data in autonomous system can be perception data, where we use to collect data from the cameras, from other sensors like lidar. The data can be system-wide data, which is representing the entire system, like the traffic conditions on the roads, the weather, and environmental factors. The data can be anomalies and other edge cases like accident and some other rare cases. So when we want to collect and generate data that is synthetic for all these different categories, we can use different types of neural network architectures, and some of them are here on this slide: variational autoencoders, GAINs, flow-based models, and diffusion models. Variational autoencoders, they generally take the input data and transform it into the latent space, and then from the latent space, it generates new data. GAINs used to work with the encoder-decoder architecture. So there is an encoder which transforms the data into the latent space, and the decoder decode it. And there is a generator and discriminator networks. And if you have read about it, so it works on a game theory model to generate new samples. There are flow-based models which just work on the distribution of the pixels of the input data or input samples and generate new data. But diffusion models are something new in the game, and they perform extraordinarily well as compared to the other models. For example, when we use GAINs for synthetic data generation, here are just a couple of examples. So we can apply GAIN to convert any RGB color images to thermal infrared images, like as you can see on this slide. Similarly, we can use GAIN networks to denoise blurry or noisy images, and we can generate new clear images from the noisy images using GANs. But the problem with the GAIN is, although it can be applied in several applications, the GAINs are highly unstable when we are training them. GAINs are also not very reliable. Their results are not of very high quality. The images or the outputs which they generate are not of very good quality. So due to these limitations, we are moving ahead towards the diffusion models. Now, diffusion models are a new category, new types of neural network architectures used to generate new data. They are actually inspired by the physics of the thermodynamic systems. So in a way, in an example where we put a drop of ink into a glass of water, and the ink molecules distribute over the period of time and finally become equally distributed in the whole glass or water container. So in this way, the pixels, if we take these molecules as pixels in any image, the diffusion of pixels in the whole image can let us, okay, we'll put it this way. So when the molecules of ink are distributed equally in the whole water glass, it becomes almost a noise. So the color of the water might change slightly, and the original shape of the molecules completely disappear. But somehow, if we can reverse this whole process, we can regenerate the original shape of the ink inside the water, which could be slightly different, but that would let us generate new shapes. So similarly, if we take pixels as molecules, we can generate new images, which will be explained here in these subsequent slides. So the diffusion process generally works in two phases. In the phase one, we take an image, we run it through a forward diffusion process to convert this image into a complete Gaussian noise. And then we take this Gaussian noise and pass it to the reverse diffusion process to generate new images, which looks like the original images on which the diffusion model has been trained. Now, taking ahead for further explanation, in forward diffusion process, we take an input image, let's say X naught, we progressively add Gaussian noise in different steps. So after every step, the image loses its distinguishable features, and when the time steps reaches a higher number, let's say towards infinity, so the input image completely disappears and you get a pure Gaussian noise. Now, if we can see this whole process and we can train a model, a neural network that can learn how at each time step the noise has been added and how it transforms the image from, let's say, from the left to the right. So if we can learn this whole process, and if we can learn this noise addition at each time step, and then we can reverse this process, which is called the reverse diffusion, so we can generate new images which will look like the original data set on which this model had been trained. So we train a neural network to predict the noise at each time step. And then in the generation process, we take just a random noise, nothing else, just a random Gaussian noise, and iteratively pass through these steps, remove the predicted noise to create a new sample, which looks like the original data. So diffusion models are actually Markov chain of diffusion step, which slowly add random noise to generate new data through this reverse diffusion process. Now here is how diffusion model works and create a simple shape of data. And if you want to look at a very complicated or complex example, here is one example from the Meta's diffusion model, how it generates new data of high quality. Now, there are a couple of notable diffusion models. Some of them are listed here. The DDPM, denoising diffusion probabilistic model. This is a kind of model which was somehow the first diffusion models which got a lot of attention, and it is completely stochastic. So you can always generate new data, but the data will not be exactly the same as the input data. So it's not deterministic, it's completely stochastic process. It's good for data augmentation and training robustness. You can use it in exploration heavy domains to completely generate new amounts of data. The data is of high quality, but this process is very slow. So you can use it when you want really high diversity in the new data, for example, creative art. The DDIM, denoising diffusion implicit models, are deterministic version of DDPM. So they are good in speed, they work in real time, they and faster generation. They also require fewer sampling steps. The outputs they produce are more deterministic, so you can always regenerate the same data samples with the DDIM. They are faster, so that's why they're also good for edge devices and limited compute budgets. The latent diffusion models is another class in a modern architecture of diffusion models. It actually this type of diffusion works in the learned latent space instead of the pixel space where the other previous two models works. LDM uses either sampling regime, so you can use it for stochastic or use it for deterministic sampling. The good thing with LDM is they are using much lower compute and memory, so you can scale them enough and they are always efficient as compared to the previous two diffusion models. Then there is another type of diffusion model. We call them conditional diffusion models. The three diffusion models which we discussed before are how they generate new types of data. Now, conditional diffusion model is not a new model, but this is just like a new feature in the diffusion model. So how we can use diffusion models to generate data that what we want. So we guide the diffusion models. We give them a kind of instruction in the type of prompt. The prompt can be a text or it can be an image to guide the diffusion model to generate a type of data similar to the prompt or similar to the instruction that we wanted. So this is more efficient. This is more useful in a lot of other scenarios where we provide labels in the form of text or images to guide the diffusion model. Now, the popular text-to-image diffusion model, where we provide a textual instruction to generate new images, some of them are listed on this slide, and you might be familiar with many of them. So like the Google Imagen, Stable Diffusion, DALL-E for the OpenAI, Midjourney, and Meta's model. They are very popular nowadays, and they normally, all of them are using some kind of the diffusion model that we have been discussed in the previous slide. Now, how we use the diffusion models, where we use them, what could be the possible use cases for autonomous systems? So the first use case, which is very important, is whenever you have data imbalance for any types of data in your autonomous system, there are some underrepresented classes or underrepresented conditions. For example, night or snow conditions are less dominant you can always use diffusion models to generate new data, and it will complement your original training data for efficient training processes. Then this is very common, very important. There are some rare safety critical scenarios which you cannot gather enough data about them. So collisions are always rare. You cannot just make collisions, real collisions on the roads and collect data of them. So you always need to have enough data, but this data is difficult to acquire. So you can use diffusion models to always generate data about the near miss collisions. If a sudden pedestrian is crossing on the roads, there's emergency brakings. These events are rare, but you can use diffusion models to generate these kinds of data very efficiently. Right. So then there's another use case which is also very interesting. So you have different modalities of data. There are different sensors in your autonomous system. This could be a camera, a LiDAR, or a radar. Now, most of the time, these data are from different sensor or different modalities are they should be synchronized with each other. So sometimes you might have the camera data, you have good quality of image, but your LiDAR point cloud data might be, let's say, not sufficient. There could be missing point clouds. So you always have a chance to use diffusion models to, complement your data and convert your data from one modality to another. You can create realistic images under varying illumination, let's say, if you want motion blurs, or if there are motion blurs that you want to avoid, there could be lens artifacts in the camera images. You can always overcome them using diffusion models, and they will give you more realistic images. For all these scenarios. LiDAR point clouds, they are always suffering from this problem. They are sparse, so they are missing points for different objects. You can use diffusion models to complement this and complete these point clouds. The density, if they are varying for different objects or different parts of the image in the LiDAR point cloud, they can be completed using LiDAR. And similarly, occlusions can also be done. Similarly, for the radar, the noise patterns and multipath effects, if they have missing or inconsistency or missing patterns, they could be complemented and completed using diffusion systems. And then another use case, domain adaptation and simulation to real world adaptation or transformation. This is very important. So diffusion models can be used if you want to, let's say, kind of style transfer. So you have data for one particular environment, one particular city or country, or let's say one particular time or weather condition. You can always use diffusion models to transform the same data to another domain or another style of the data. You can always change the data from simulation to real world. If you have simulation data from some software and you want some real world data because your actual system will work in the real world, which is not as simple as a simulation environment. So you can always use diffusion models to learn from the simulation and transform it in the real world. So a simulated road can be transformed completely into a real world road with different timing, different time of the day, different weather, and road texture conditions can be easily adopted using diffusion models. There could be a lot of other use cases for the diffusion models. We cannot go through all of them, but definitely diffusion model is a very good candidate for generating synthetic data for any kind of autonomous systems. But they are good, but not without challenges. There are still a lot of challenges for diffusion models, and there are some open problems which my fellow researchers would be very much interested to work on in their research. So one of them, which is very important, is high latency. So there is always a trade-off when we are working with diffusion model. There is a trade-off between the sample quality and the denoising steps. You want a high quality output, you have to use a lot of denoising steps in the diffusion process. And definitely more steps means high latency because your diffusion model will be slower enough. So what we are aiming at, we are more interested if we can have a diffusion model which use fewer steps. And ideally, if some diffusion model can just generate the whole sample in one step without quality collapse. So that could be a target and a research direction. Diffusion model has high computational cost. Like unlike other neural network architectures, we take a lot of time when you're training them, but in the inference stage, they are just fast. Uh, Diffusion models are different. They are computationally, very heavy, not only in the training, but also in the inferencing step. When you are generating new samples, they are denoising steps, and it takes it takes quite long time to generate new images. Especially, as I said, if you want to generate high quality of data, you need to have a lot of denoising steps, and this will slow down the process. It will give you more computational cost. So definitely, as the researchers, we are more desiring for lightweight architectures for the diffusion models. And then diffusion models generate new data. So how to evaluate the quality of this new data? This is a new direction. We need some reliable and domain-specific metrics and frameworks to evaluate or diffusion model their outputs. And this could be different. Uh, the evaluation criteria could be different in different scenarios, and different objectives could be set, different metrics could be defined. So this is again a very interesting direction for diffusion models. So for future directions, there could be many. I'm just listing this as which is connected to the previous slide as well. So we can we can combine diffusion models with physics-based, which is rule-based simulations. So this can help us simulate physical world with the power of diffusion models when we need any data that is not included in the simulation. We can use diffusion models for cross-modality generation, as I discussed. If we have different sensors, we have some missing data for one sensor, we can use diffusion model to complement and complete the data. And this is a very interesting direction for different simulations as well. Lightweight models for onboard data synthesis. So there is a vehicle running on the road, and there's a system for detection, let's say, for the road environment. We can have diffusion models installed on board, and it will always generate new data on board if it's required for the detection process. But this model should be a lightweight architecture. So these are some very interesting directions to use diffusion models in autonomous systems. So I think I'm done here. Thank you for your time and listening. If you have any question, you can continue to ask them in the Q&A session.
Thank you, Mohammad, for this very, very interesting presentation. By the way, I'm myself working on this in this area. So, well, I will certainly get in touch with you. I hope that the speech has been found interesting and inspiring also by the other attendees. Maybe for the sake of time, we can continue with the next speaker. So I leave the floor to Dixon, who will introduce Sean. Thank you.
Okay. Thank you, Fabrizio. So I'm Chen Hong Lin, Dixon, and Vice Chair of the TC Board CTSoc. It's my honor to introduce the next speaker, Professor Shen Ma. Shen Ma is a lecturer in the School of Computer Science, University of Auckland, New Zealand. He actively served in the Technical Committee on Smartphone and the Mobile Device Technologies, MDTTC. Professor Shen received his bachelor degree from Harbin Engineering University, China in 2010. His master degree from Shanghai Jiao Tong University, China in 2016, and his PhD degree from University of Auckland, New Zealand in 2023. Shen had almost 10 years of the industrial experience working as on an FPGA and the integrated circuit design engineer. And Professor Ma research focused on algorithm implementations using parallel computing devices such as FPGAs, digital design using FPGA platforms, high-level synthesis design using FPGAs, and the RISC-V core customization, including subsystem integration or customized instructions. And here is the above are brief introduction to the Professor Ma. So the title of his speech is Beyond the CPU, Dynamic Hardware and Efficient AI for the Next Generation of Mobile. I would like to leave the floor to Professor Ma. Thank you.
Okay, thank you, Dixon. Thank you for the introduction. Okay, so I'm going to share my screen. Hey, I think everyone can see my slide.
Yeah.
Yeah, all good? Okay, so today I'm going to share one of my topics called the Beyond the CPU, Dynamic Hardware and Efficient AI for Next Generation of Mobile. And I'm Dr. Sean Loima, and if you look at the history of computing and the mobile devices has been actually trying to chase PC because it chase what PC did yesterday and the phone does today. So with the rise of these generative AI recently, we have kind of like hit a wall because when we seen those very power hungry models are doing right. They really need massive and kilowatt burning GPUs to do the inference. So the question today is more like, can we really fit that power into a pocket? So my talk is titled Beyond the CPU, right? So because it brings the true AI to the next generation of mobile. So we cannot just build faster processors because probably the architecture of these processors, or we see central processing unit, could be not really doing something like AI tasks. So we need hardware that can adapt those new changes. So today I'm going to show you some like promising ideas because I'm just a new lecturers, young professionals, and trying to find a way to do the research probably in the next few years. So that's promising idea probably may be the key to breaking the mobile efficiency barrier. All right. So here's my plan for today. So I'm going to divide this talk into two parts, and the first we call the why. So I'm going to explain the mobile AI crisis. I will show you the challenges we're facing when we trying to simply put a PC level AI model onto a phone or any mobile device. And second is we go phase two. I will present the solution. It could be a potential solution. So I will introduce we call the reconfigurable hardware, and it's a promising way to rewire hardware in order to adapt those whole things to AI tasks. So let's start with the phase one, the why. All right. So before we dive into the phase one, I just want to ask you a very simple question. So you don't need to answer me, but you can probably just answer in your mind. So think about the last time you bought a phone. So what did you look for? So usually the direction is very clear, right? So we want a faster CPU, and we want probably more storage for our photos. We just take, right? So and we want more memories. Probably it's easier to or faster to open apps. So for the last maybe around 15 years, this has been kind of like a formula. So we just want more of the same thing. So, but you ask yourself, is this linear growth enough for AI revolution? Or we say, if we just make maybe a CPU 10% faster, can we suddenly run a human level intelligence in our pocket? So I actually, personally, I believe the answer is no. We probably need to innovate something which can really run AI in our pocket, right? So let's stay back and maybe broadly look at the timeline of computing. So first, if you still remember that it were been decades ago, and so we have a PC era. So the computers are really powerful, right? So because we just simply to plug the whole thing into the wall, and we don't need to worry about the energy. So we just add the bigger files and the bigger GPUs, and basically we can say that we have a limited power. We can do anything we have, but actually we don't do any AI stuff here. Well, then since 2007, we enter into I call it the mobile era. So the smartphone actually became the center of our lives, right? So we have to treat treat power for portability, because we prefer something could be portable, that can be easily to be put in our pocket, and we easily to take out to see something from the screen. So, but we have a limitation. So we have a limited batteries. So batteries will be constrain everything. So we have limited batteries, and of course there's no cooling fans in our cell phones. And we can do probably some simple AI, or we like the Siri from Apple, or some Face ID or Touch ID, something could be related to AI tasks. All right. So now we are at kind of like a new turning point. So we want to run general AI like ChatGPT on device, not from cloud, right? So we want to run something in our phones or mobile devices, but there is a wall, and a modern AI model actually need hundreds of watts to run fast. Well, a phone usually have what do we have? We only have 3 and 5 watts, and that's also our thermal budget. We cannot increase more than that, otherwise there will be the phone will be too hot. So this is the crisis. So we cannot just shrink the GPU anymore, because once we shrink the GPU or any kind of like AI acceleration things, well, the performance also drops. So we need a kind of like a new architecture which can accelerate the AI, and also could be enough to be embedded into a mobile device. So well, this year actually our group focused on a simple question, and can we really make a simple single core CPU efficiently, running some deep learning works? Actually, we modify a very standard RISC-V core, and well, I'm proud to share this work, because the work actually we won the best paper award at the IEEE MCSoC symposium this year. And the hardware innovation is that our solution actually trying to create a customer instruction. We call it the P.P4. And as you can see here, that we, instead of wasting of 32-bit register on one single number, we actually pack 4 different eight 4-bit integers. So every integer has 4 bits, and we pack eight that kind of integers into one register. And this allows us to perform basically 8 multiply accumulation operations in one single cycle. And now looking at these diagrams, well, the implementation seems very easy, because we just simply should chop until we have 8 same long integers, and we do the MAC operation together. But actually, the hardware was a little was just half the battle. We spend significant time on the quantization strategy, because since you're trying to compress a model from maybe fully 32 bits to 4 bits, there will be quite a lot of trouble. So we cannot simply to jump to 4 bits precision without breaking the model, and we trying to develop these we call adaptive gradual quantization method. We carefully, probably stepping down from 32 bits and to 16, and then to 8, then to eventually to 4. So this will make sure that we keep the very high accuracy while also have this gaining speed. So the result, of course, there's since we already have the eight Mac unit running together, so we have kind of like a 8 times parallel Mac operations per plot, and that will be can be run for the vision transformer, and compared to the original RISC-V cores, it has 8 times speed up. But of course, we have the limitations here. I just want to be, we must be honest, because well, this works perfectly for some specific tasks like a vision transformer, but it's not enough for the large language model. So why? Because the large language model or LLM are too big and too diverse. So that's the probably we need some hardware flexibility. Otherwise, we cannot go further. All right. So if implementation large language model actually based on especially based on transformer is inevitable, we need to know the actual size or the physics of the large language model LLM. And now I want to invite you to do a little bit of quite quick calculation with me. So if we want to implement a typical large language model on what hardware do we actually need? So let's assume that we only do the inference only, and well, we are running on a model and not training it. And first, look at the well, the left box. How much VRAMs or VDRAMs do we need if we have a GPU? So it is not just the model weight actually. So it should be model weight plus the KV cache and the activations, a little bit of framework overhead. So this is roughly the things we need to consider when we trying to store the things into the VRAM. And to calculate this, first we need to take the parameters multiplied by the bits per parameters, and well, it depends on what kind of the data type you choose. And after that, we need to multiply probably 1.2 to 1.5 to account for the overhead, because we need to consider something to accelerate the whole inference. So we have some overhead. So after that, we can estimate how big we need for our memory. So this is a very rough way to estimate how much VRAM we need to inference one large language model. And now the red box actually shows the speed limit. Well, it's if we want to a certain speed, like tokens per second, so we need a specific amount of the memory bandwidth. So the speed is inversely proportional to the model size. Well, the model size actually matters a lot. So the bigger the model, the harder it is. It's harder it is to move, right? So finally, if we look at the origin box, though the numbers are derived from the formula above, and they are not a very precise result, but it's still good enough to know that if we want to run, like for example, 8 billion parameters model, like the Llama 3 8-bit, and at like for example 14.16 data type, so probably we need those kind of the RAM or VRAMs in order to load it. And if you also we probably need 160 gigabytes per second memory bandwidth to achieve 10 tokens per second. So this is something we call the hard flow. It's the hard flow requirement for mobile hardware, right? So it's kind of like it's impossible to have such a big DDR or the main memory, right? So you probably all ask, why do we just use some smaller models? And it is true, and we have models with only 8 millions. And here, just list some of the open source ones in case you're interested. But what I can tell you that is these are small models are good for some structured tasks, like classifying or doing some simple translations, but they like some the how they cannot reason, they cannot chat like ChatGPT, or cannot chat creatively. They cannot understand complex contexts. So basically, that is not going to work if we implement those sort of small large language model onto our mobile devices. So those small models are not the full solution. So how is the industry reacting? Because I'm basically I'm from the I worked in the industry for quite a long time, and I know a little bit. So let's look at the Apple. So first look at the the left panel here. So this is the for iPhone. So if you follow this blue line, for years memory size kind of like was flat, but in 2024 and it suddenly jumped to 33%. So why? That wasn't for the better gaming, and that wasn't. It was actually kind of like a mandatory is a must change. So to run AI on device, if you still remember that the Apple Intelligence support any phone from iPhone 15, so to they can run some AI on device, and the hardware actually face a hard flow requirement. And according to, I guess, probably Apple think maybe 8 GB is the the hard flow requirement for their memory. So this is the capacity constraint. And now look at the right panel of the for iPad. And this is more interesting. If you look at the right line here, well, it's separate from the this is the memory bandwidth growth, and this dotted gray line, these represent the CPU performance growth. So actually, the insight is very clear. Well, in the currently, it doesn't matter how fast your processor running or not. Actually, it is what matters the memory bandwidth, the memory size that matters. So Apple, something like some industry companies like Apple, is trying to redesigning the chips. They're trying to redesign the chips to keep up with the AI fad, and this is the speed constraint. So it seems like this current design works, but actually it sacrifices some user experiences because the main memory are used for some like to store some applications where the users are running, right? So if we try if the system trying to run something like AI models on using these kind of like memory, and will lead less free memory for users app, right? So personally, I don't think it is a good idea. So what other options we do have? Actually, here are the topics. We have the reconfiguration architecture. So there are two main contenders. Firstly, the FPGA, we call the field programmable gate array. The second, we call the coarse-grained reconfiguration architecture. Here it's just we can simply skip it because they just tell you how to program using these FPGAs, and also we also have the CGRA, the coarse-grained reconfigurable architecture. Probably you heard of the another name called NPU, the neural processing unit, right? So normally the NPU will embed it in your laptop and the phones, and for AMDs here they have the NPU the derived from they call the AI engine or AI engine machine learning, these kind of things. So compared to the FPGAs, the only difference is that they have different tails, and those tails can be programmed. And it's because it's the coarse-grained reconfigurable architecture. So which means that it's less flexible. All right, so it's less flexible. If a new AI algorithms came out tomorrow, and which probably doesn't fit these blocks, the CGRA will struggle. So here we have the three-way battle. When we talk about the how to implement the AI onto the mobile devices, normally the batch number will be equals 1 because only one user will start the request for AI tasks. So to understand which one will win, I just simply list FPGA could be one of the potential way to work on our mobile devices, because compared to the GPU or the CGRA, it has a better ultra very very low latency, because this will affect the user experiences, and also it is it's very flexible because if you have experiences of programming on RPG, so we can simply to create like a 3-bit quantization instead of the 4-bit or 8-bit, those kind of the standard data type. We can just create it like 3-bit, 5-bit quantization, these non-standard operators. And for the CGRA and for the GPUs, they cannot adapt. So because they are already hardened silicon. So this is a good thing for the FPGAs. And now we're going to move to the phase 2, and because we try to establish the FPGAs because the FPGA can offer the best latency, right? And we discovered before we move on to the large language model, we found that the large language model has 2 different stages. We call one is preview, the other decode, and they have different type of the operations for different different stages. And here I just cut the short. So the preview phase actually, what is preview fetch? This is the when the models read your promotes. To write something promote, and they read it, and they process all the input in parallel, and you can see in the roofline model. So, well, it means that on the this it is the compute bound. So what does it mean? It means that not only those your power or the actual performance for in this case, it depends on how much calculation power you have, like the floating point calculate power or whatever. So this is very easy to optimize as long as we have enough um, calculation tiles, or we can easily to accelerate. The second part is we call the decode phase. So decode phase, this is the when the model trying to read the answer. It generates one token at a time, and this creates a bottleneck. So this shift from being computer bound to memory bound. So the memory bound means that we normally the performance depends on the memory bandwidth. Right. So here I give you a very visualized example, like we trying to when we trying to do the profile, and that's pretty easy. They can do is the very quickly. They happens instantly, and but when we doing the decode, they just trying to enter a decode loop. It has to generate a then robots and then may something like that. It cannot calculate may until they finish a robot. So it's very strict sequence. So this give us two different ways we can try to accelerate those accelerate the decode part. I think probably if you have experience in that, you can easily to know that we this very traditional way and the very typical way to accelerate that. So overall, well, what I'm trying to say that the large language model actually have two stage. A preview stage, especially to the text to large language model, it has preview stage and decode stage. They have to be considered separately. So here I just want to show kind of like a very quick things. So this is about the using the partial reconfiguration. It's about what we call the dynamic partial reconfiguration. And this paper actually proposed a time multiplexing hardware. Because they only have one FPGA chip. Firstly, they trying to run the preview, and second, they will run this decode stage in the same FPGA. So this, but we have to consider have this IPG technology to do this swapping. Otherwise, it's impossible. So the IPG can become computer monster to handle this promotes at the first stage. In the second stage, decoding stage, well, IPG can be regarded as the itself as the trying to rewire everything to increase the bandwidth as a bandwidth specialist. So yeah. So with this kind of technology, we can have something like we can run faster and smarter. But if you look at the big picture, so the big picture is shows the previous designs on IPGs, especially on PGs, and also something on GPU. So this chart shows a very comparison between the IPG and GPUs in terms of throughput, and throughput versus the power consumption. We call the unit is tokens per second, and this is the watts. So the information collected shows that the PTSwap or the other probably you're familiar with that. These two pairs are similar because they are trying to run the same large language model, but this pair actually was implemented on the GPU, and these two are on FPGA. So the GPU dominates basically they are very power consuming. They require more than 100 watts, and we don't need to talk about it. But for the IPG, actually, we prefer to seeing any implementations under 10 watts because that's probably the promising implementation we're going to use for our mobile devices. So but currently we can still see that the performance is not really good because the most of the implementation we set in these areas, which means that the throughput or tokens per second is really not good, but the power consumption is okay. So yeah, so this is the but if you compare to these two groups, we can say that the IPGAs actually is a better platform compared to GPUs running on large language model because they trying to separately consider two stages in large language model because we have two preview and the decode stage, right? So at the bottom at the this bottom here, so this actually shows the future and because the battery life is always the king for mobile devices, and we cannot just easily to jump into these areas because we still need to fighting against some challenges. I think probably as one of the researchers, we're just keeping pushing on our design until one day we will embrace a more energy efficient AI model running on some mobile devices and will reside in here. So yeah, so to summarize my talk today, so let's look at some three key takeaways. And the first is about the reality. So we identify the problem, the bottleneck for mobile AI, because it's not how fast your CPU it is the memory wall. As we saw, because the mobile devices serve only one user, and the standard hardware actually leave the memory bus starving. All right. And the second things I talk about a little bit solution is the possible solution. We prove that the static hardware is not a good platform for large language model. We probably need to consume the the reconfigurable hardware like IPGAs or CGRAs because we need to consider preview and the decode stage in the large language model. And the last one is about the future. So we are entering what I'm trying to say that we're trying to entering the era of co-design. We cannot simply to increase or build faster chips. We must redesign the math to fit the chip as well. So to run this human level intelligence on a battery powered devices, we need to think about on both ways. So this is the era we call adaptive AI hardware. So yeah, so thank you very much for your time, and I'm happy to take you any questions.
Thank you, Sean. I think this is really the future, as you said. So, thank you again for this very nice and current speech.
Oh,
I think that it's now 2:07, so we have slightly run out of time. So I think that the best things to do now would be to thank our speakers. And I think that they shown their contacts, but in any case, you can contact either directly them or if you want to write to me or to the officers, they will certainly create the connection. So thanks again to Mohammed and Sean for this very nice speech. Thank you, Dixon and Yogesh for moderating with me, and thanks for the attendees. The next webinar will be on February 27, same time. So details will be posted this afternoon. So thanks again and cheers. Bye bye.
thank you, thank
Bye-bye.
you.
Happy New
Thank
Year.
you.
Thank you. Bye-bye.
Yeah.